There's the mechanics of how to calculate it, but then there's also kind of what we're going to do with it. So let's say that I had two vectors, and I'm going to let A be equal to the row vector 1, 2, 0, and B will be equal to the row vector 3, -1, 1. So calculating the dot product of A dotted with B, that's probably the most straightforward thing we can do with dot product. So when we calculate dot product, we multiply the entries that are in the same position. So I'd have 1 times 3, and then we add that to the next set of entries in the same position. So 2 times -1 plus 0 times 1. Now, geometrically, dot product has some meaning. One of the ways that we put meaning to dot product is through the law of cosines. So you're not expected to have memorized the law of cosines or the proof of the law of cosines, but one thing that comes out of it in relation to dot product is that we have a geometric formula for A dot B, which is equal to the length of A, or the magnitude of A, times the magnitude of B times cosine of the angle between the two vectors. What this allows us to do is to actually calculate the angle between two vectors, even if we aren't given a picture, or in this case, if it's in 3 dimensions, trying to visualize what that angle between the two vectors is would be impossible for me, nearly impossible for some people. So let's say that I wanted to calculate the angle between these two vectors. First thing I want to do is just to finish off this value for the dot product. That's 3, -2 plus 0. So I got 1 for the dot product there. So if I went to calculate the angle between these two vectors, I'm essentially trying to find cosine of theta in this equation. So I now know that the dot product value is equal to 1, and now I'm going to need the magnitudes of the two vectors. Well, the magnitude of A, or the length of A, I'm going to get by taking the square root of the squares of each of our components. So that's going to look like 1 squared plus 2 squared plus 0 squared, square root of 5. And if I go to take the length of B, or the magnitude of B, it's going to be the square root of 3 squared plus -1 squared plus 1 squared, 9, 10, 11. So that's the square root of 11. So that means in terms of this equation, I have that my dot product, which equaled 1, is equal to the square root of 5 times the square root of 11 times cosine of the angle between them. So if I want to get the angle by itself, 1 divided by the square root of 5 times the square root of 11 is equal to cosine theta. And from here, we're going to have to use a calculator. So to get that into an actual angle, I do theta is equal to cosine inverse of 1 over square root of 5, square root of 11. There's one other thing that kind of geometrically we do with the dot product, and that's the vector projection, or the scalar component of the projection. I don't really know what these two vectors look like. I'm just going to fake it. So if that's my vector A and that's my vector B, then we call the projection of A onto B. We think about drawing this right triangle kind of between A and B, and whatever this distance is here, that's the component, or the scalar component, of the projection of A onto B. Now, using geometry, we know that we can get that. Here's theta. We're really looking at kind of the length of these two sides, or the adjacent and the hypotenuse. So I know that from this triangle, that component of, that scalar component of A onto B, or the comp of A onto B, that's my adjacent side. And if I divide that by the length of the hypotenuse, or the magnitude of A, I'm going to get cosine of the angle. Well, using what we know about the dot product, if I multiply that A over here, then I almost have something that looks like the dot product. Kind of ran out of space over there. So if I rewrite this, and I've got that scalar component of A onto B divided by the magnitude of A is equal to cosine theta. If I multiply that magnitude of A over, then that almost looks like my dot product if I take this and multiply it by a magnitude of B and then also divide by a magnitude of B. So the other way to look at this is that my scalar component of A onto B is A dotted with B divided by the magnitude of B. And then if we wanted to make that, if we wanted to turn that scalar component into a vector projection, then I'd want to multiply this by, to turn it from the scalar component to the vector projection, which we would write as the projection of A onto B. We would then multiply by B as a unit vector. Two last things that I'll say about dot product. This equation also has two specific consequences when my vectors are pointed in specific directions. So if my two vectors are perpendicular to each other or orthogonal, or there's a 90-degree angle between them, cosine of 90 degrees is 0. So if the dot product is equal to 0, then the vectors are orthogonal or perpendicular. If those vectors are parallel, then that would mean that the angle between them is either 0 degrees, or if they're parallel but kind of pointed in opposite directions, 180 degrees. Well, cosine of 0 is equal to 1, and cosine of 180 is equal to -1. So that means that if my dot product, or if my dot product divided by these two magnitudes, right, if cosine of my angle works out to be 1, then I know that those vectors were parallel. And if cosine of theta works out to be -1, then I know that they were parallel but in opposite directions. And in general, anytime my dot product is negative, it's going to mean that our vectors generally are pointed kind of in opposite directions. So if I redrew this picture such that my B is going this way and my A is going this way, if I look at the projection of A onto B, I'd kind of have to extend this B out into imaginary space in order to get that right angle. So I know that if I took the dot product of these two vectors, we'd get a negative value.